We did some experiments over a test bed. So these three vehicles are actually downstream human-driven vehicles. These two are human-driven vehicles. This is CAV. So the three vehicles will stop here, and this will just pass the intersection without stopping. So this is not simulation; it's real-world tests. So, it's some of the results are pretty good. Look like this one. You can accurately predict when this vehicle is going to start up and join the queue without stopping. And we're still in the process of comparing that performance with Ewell's models or simple model predictions. Hopefully I can report that later. But and then we also, with some recent effort, we also did some AV lane changing experiments. So AV lane changing is like it's not just longitudinal control. It has longitudinal control, but it also has lateral control. So it's again one vehicle. AV makes the lane changing in response to some surrounding autonomous vehicles. How much time do I get?
You still got time? Yeah.
All right, sure. So basically, the things this is real-world experiment. We use some data to do some to predict to calibrate some conformal models and to use that to predict the acceleration and deceleration impact to surrounding vehicles. And then we also adjust this vehicle's trajectory, lane changing trajectory in real time. And only by real-time adjustment you can absorb the impact of uncertainties. So we did some experiments like this with multiple traffic scenarios. This is one traffic scenario. So this is a CAV, and these three vehicles are actually AV. And to sort of predict, to emulate the scenario when there is shock wave on the current lane. Slow down shock wave on the current lane. So this vehicle will follow two vehicles and then find a proper opportunity. And once the gap allows, the AVs can merge into this target lane. Okay, and we also did some simulation to hope to reproduce this process. So remember, these vehicles are all human-driven vehicles. They're not programmed. So this vehicle has to be adapted. So we also have some abortion mechanisms too. In case your prediction is not correct, or is unsafe, just abort the lane changing halfway. All right, comparison between HV and CAV. Okay, we actually compared HV lane changing with CAV lane changing. We find that the speed standard deviation and maximum acceleration can be much reduced with CAV control. Human driving vehicles are not that stable. And then last I'm going to talk about some recent exploration with deep reinforcement learning. So again, this problem is like we know the downstream traffic trajectories, which can be perceived by sensors from autonomous vehicles or passed from connected vehicles. And how do we control an upstream autonomous vehicle, right? So we have offline data like the data set I showed, miles long, the 13 vehicles. We can pick a few, and then we just start from the back in the offline data. We can start the training process. Assuming that new future data is available, then you can assume that scenario that these three vehicles are at this point, and there's a CAV following them at this time 0, and then you can do. With the input window, you can train some control policy, which is the neural network. We actually use a deep neural network. And then apply that to policy, then the vehicle is going to go for one step and for another step, and so on and so forth, until it goes to a certain long window. And then we evaluate the performance of this vehicle over this window based on the mobility and safety and sort of the driving comfort matters here, and then we can optimize on neural network parameters with cross entropy method. That's a method we use to optimize these parameters to find the best policy, and then we can apply that into real-time control. So it's like real-time control. It's like if you just apply that policy, and you can go to the next step. And then you can have more observations. And once you have more observations, you can actually move the training window longer. So you can do the training and adaptively. So sorry, this is reinforced. So, and you can do the training and evaluate that process again and again to dynamically improve your neural network policy. So, and we did some experiments, and remember that all these data, the downstream trajectories are from the real-world data, so it's not simulated data. We did some comparisons with a proposed deep neural network-based controller, and then that's a proposed, it shows with brain curves, and also ACC controller, that is a linear ACC model, scaffold model, and also human-driven vehicle data. We can pick up the actual human-driven vehicle data to do the comparison. We find the overall performance of the proposed controller is actually we don't see the detail. It has less has better reward function and less safety violations. But there are some sensitivity issues as well. You're going to see sometimes the safety is violated very badly for the neural network. So you have to do some, probably need to wrap around with some physical model to control the acceleration, or have some emergency brake around it. And then we tried, the information from different numbers of different numbers of vehicles, and we see that with more vehicles involved, your performance would be better. When we try different windows, input windows is like the input size. We don't see a significant difference. That means probably the history way back doesn't impact the direction that much. So some thoughts actually, this learning we're doing is just a pure based on standard deep neural network. But actually, convolutional model, it's a very simple neural network, right? We were thinking whether we can build some neural network structure based on convolutional model that expounds the convolutional model, but also take advantage of the physical properties of the convolutional model. Some thoughts: reinforcement learning is a training more accurate prediction, that is reliability and robustness, needs some further investigation. Mathematical programming is exactly requiring quite some computational resource. Fast heuristics, fast data means industry practice. Okay, so it's actually broken false if you listen to it. So in future research directions, so we think that we can go from more into the microscopic, or that is a powertrain of the vehicles. I'm particularly interested in the electric vehicles. That's the trend for the future autonomous vehicles. And if you go up to the bigger scale, into the microscopic transportation, you can look into the macro scale issues. We've already done some work about imagine routing, capacity analysis, and actually, I tell you, FDOT, the state DOT are pretty interested in this kind of work for the capacity analysis. And we also have a project about accuracy for the federal level. And also we want to extend it to sensors. We have all sorts of different sensors. Like in vehicle sensors, you already have video, LiDAR, radar. And you can also add some other sensors like road frictions and other like visibility, other environment sensors to on the one hand, it improves the controllability of autonomous vehicles. On the other hand, it can provide DOT with good information for safety warning. Actually, DOTs are pretty interested in that. Cybersecurity. Trajectory control is thick inputs from connected vehicles. All right, so last is we have some test bed constructed this year with access to different test facilities like Suntrack high-speed track, push gardens, runway, and USF track, and we did some good experiments. With that, we've got some attracted some high-profile people visiting us, legislatures, government officials, business leaders. And finally, I acknowledge my collaborators, and colleagues, and also funding agencies to put it together. With that, I thank all of you for your attention. I'm happy to take any question if there is any time.
Thank you, Xiaopeng, for such an interesting presentation. I think we ran out of time.
Yes, but we can, if there's some questions in the lobby. Yes, thank you.
All right, thank you.